Professor Narayanan. He's an expert, he's a distinguished speaker for today's session. He's an expert in the fields of computer vision, computer graphics, and parallel computing. At the Center for Artificial Intelligence and Robotics, he led a computer vision and virtual reality group and contributed significantly to VR applications for DRDO and defense. He then founded the Center for Visual Information Technology at IIIT Hyderabad, and they work in computer vision, graphics, and medical image processing. He's currently the director of IIIT Hyderabad. Narayanan's groundbreaking work spans various domains, as you might be able to tell, from 3D reconstruction and structure, structure from motion to machine learning techniques, and more. So over to you now to tell us about computer vision.
Thank you, Aruni. Good morning, good afternoon to all of you. It's a pleasure to be here again. So I will try to tell you quickly about something that you see every day. All of you are using this every day, computer graphics, for instance. So I want to ask you a question first. You I'll show you a few pictures. Have you seen this kind of pictures? Go back. Yeah. Have you seen this kind of picture? How many of you play computer games? Nobody plays computer games? So what is this picture about? Which game is this? Nobody knows? So similarly, the next one, just click once. What is this? Just click once. Say okay, hello. Yeah, what is this you are seeing? You know what this is? Which movie is this? Okay, so are these photographs? Are these photographs? Do you think the photographs somebody took with the camera? Click once. Click, please. So these are fully computer generated. And how are they generated? That's the story of computer graphics. So in computer itself, computer is a device that can store, process, and reproduce any kind of things. You today make documents on a computer, you make images on a computer, you make movies on a computer, you make everything on a computer. So a computational process is abstracting something that you want to do, somehow representing it using the zeros and ones that computer directly understands. And once it's represented, you can process it, you can manipulate it, you can enlarge it, whatever you want to do, you can do. You can create your document, and then you want to print it. A document you will print, a scene you will render and show as a photograph, and so on. So this applies to everything, documents, pictures, movies, people, scenes, etc. It can also represent physical objects, or at least somehow represent it. Scenes, that is a scene like this, or a game world. How do you represent that? Okay, and their appearance. That is what is computer graphics all about. So scene in a computer, next. Yeah, so what you do is you think, if you want to create a world like this, or a room, your room you want to convert into computer representation, you have to first think, what do I want? I want a table here, a chair here, a light there, a fan there, a window here, and so on. And then you represent all these on the computer. How do you represent a table and a chair and so on? You use usual primitives. You can use standard small shapes like things that spheres and boxes and cylinders and cones or triangles and rectangles and so on. And once you have them, you use a computer graphics system. This is where computer graphics come. It simulates what you as written there, a pinhole camera. Typically all computer graphics systems use pinhole camera. We will see what it is. But you look at the scene, the lighting, the objects, the viewpoint, and generates a view. A view like this. It's a very simple scene of a few synthetic objects, not a real. It's far less rich than a scene like this. If I want to simulate or see a scene like this, far more complex. And that's where the effort is. Next. So all this happens on a pinhole camera. A pinhole camera is just this. This you would probably know from your high school or school days, if you have a box and with a tiny hole in it or a lens on it, and you have a scene outside, will be projected, will appear on the far side of that box, as shown here, because light rays travel from every point of the scene, in this case that caricature tree, every point of the scene or the tree, light rays travel. Some of them will go through the pinhole, which is an infinitesimal, very small size hole, and it will fall at the back where it will create that some color. And at the end of, since all these things come, you get a tree on the other side. But how does this tree look? Is this tree looking straight? Is this tree looking straight or inverted? It's ulta. Because as you see there, you can see the physics of why it's getting inverted. Because that, the rays from the top go to the bottom side, rays from the bottom go to the top side. And here is mathematically you can represent this. The origin of that X and Y axis meeting is the pinhole, okay? And the image is formed at distance d from it. Usually that image will be formed d units behind the camera. But I can, mathematically I can put it ahead also. The only advantage I get by putting it ahead is it won't get inverted. Seedha ho jata hai. Okay, so but mathematically the same. You can think of similar triangle which is at the behind. And you can see the XP, which is the XP, YP are the coordinates of this projection that is on the picture. XP will be the X in the world divided by Z multiplied by D. This is a simple triangle or similar triangle equation. This will be the X axis as is shown, an X coordinate of the picture on the image as shown here. You can imagine a Y axis that is coming out of this the screen, and that also a very similar behavior. Okay, because the inversion is not just top down but also left right. So this is a simple method of a camera, and this is what a computer simulates to do images. Next. And what go back. Yeah, and what you do is, in computer graphics, you have to represent things in terms of very small entities, or it is usual. A triangle is a basic entity. A triangle is a very small planar shape, okay, with any three vertices, 3D coordinates will form a plane. It cannot go out of the plane. With fourth point, you may not lie on the plane. So you create a small triangle, which is a part of the tree, and that will be mapped to an inverted triangle on the image, as can be seen there. And this is the basis for all computer graphics operations, most of the computer graphics operations. Next. So you divide. There is one technique of computer graphics called rasterization. I mean, this is a big word, but what it does is divide any object that you want to represent and draw, every object in a scene, in terms of small triangles. See there, you can see a bunny, a rabbit shape. It can be represented with large number of triangles on the left with all kinds of nice smooth detail, and a fewer number of triangles in the middle. You see some detail getting lost, and very small number of triangles on the right where the details are even less, but you can still see the shape. So you can represent a rabbit or a table or a chair, etc., as in terms of 1,000 triangles, 2,000 triangles, 5,000 triangles. That's a number that you use. Today's games will probably use several million triangles. Okay. Next, after that, project each of the triangle one by one to the image using exactly what you saw in the previous slide. That pinhole equation, you can find if one triangle has X, Y, A, B, C as the coordinates in the world, you'll have some A prime, B prime, C prime on the image. Image is a plane. In the world, it's a 3D. Here, it's a plane. Okay. Next, and then one problem is two triangles may intersect or may project to the same region in the other side in the picture, because if when I look from here, several objects are in the same direction, so they'll all project to the same side. So you have to make sure that the frontmost object or frontmost triangle is visible finally. Okay, it's not others are all occluded or hidden. Next, and then appearance doesn't depend. I mean, what you see on the top also is rendered bunny, but that doesn't look very interesting as much as the one at the bottom where you added some light, some shading, some colors change. So it looks a little bit more interesting. Okay. So you are essentially simulating the physics of how an object in the world is projected onto a camera with a pinhole camera, or ordinary simple lenses can be approximated as a pinhole camera. And this you have to do again and again and again, or for the whole scene, and you will get this. There's another way of doing the same. Okay, this is the earlier is called rasterization, where you start with think of the world as built of many, many triangles. For each triangle, you find out what is its projected or reflected points in the image and do something there. The other operation is you think of from the camera. I have a camera. This camera is 1024 by 1024, or you say 2 megapixel, 4 megapixel, 8 megapixel. Each pixel is a small point in the image. And camera is a pinhole camera. Think of a ray. Think of one ray, mathematical ray, that starts from the camera center, goes through one of these pixels, and goes out into the world. And if there are 4 million pixels, there are 4 million cameras, 4 million rays going from the same center of projection, that is the pinhole, towards the world. Now you look at each of those rays, look at one ray at a time. What does the ray see? What color should that ray bring back? I mean, I'm sending a ray outside. In reality, light rays come from light sources, hit all kinds of objects, reflect, and finally some of it comes to the camera. Okay, and what does each ray bring? What color or intensity does each ray bring to the pixel or to the film plane? That's what you can think of sending these rays out and looking at the world. Next. Each ray hits an object. Okay, it goes, the first object that is closest to it in that direction, it will hit. There's an orange sphere there. Once you hit there, you can either say, okay, this is an orange sphere. Okay, that sphere is either sphere or a few triangles. I hit that and I say, I hit the orange sphere, so I should give an orange color to that pixel. That is one way. If you want to do more realistic thing that you want to do, you have to say, how does that point that I hit on the sphere, how does this get color? It has orange painted on it, and so some orange may be there, but it also has light falling on it from light sources, all kinds of light sources. If you have an orange object and it has a green light, maybe the orange object will absorb all the green and nothing will be coming out of it, so it will look black. Okay? You know that. You know, if you have a red object and a green light, that object will look black. A red object and a white light, the object will absorb everything that is not red and reflect only red, that's why it looks red. So you have, at that point, what happens? What kind of light falls on that object, the point where the ray hits? You look at the physics. Where is all the light coming from? And what are the colors? And what is the color of that object? Together, you combine all these and say, what will come to the camera? Okay? Now, this ray, the light comes from light source as a bulb shown here, but light comes from other place also. Next. So to do that, where at object point, wherever you hit, you can send many, many rays out to light sources, to other objects, etc. So you can see there, I shown the eye there as a camera. The ray, one of the rays on the top, the left ray coming from the eye, it hits that circular object, and you can get some component from the light source. One ray goes to the light source and says, okay, this much comes from the light, and I will combine that with whatever the color of the object is. Then if this object, that ball, the first ball is a shiny object, it's like a nice metallic object, some world will be reflected on it. It won't just see its own color. If it's a mirror, it's a very shiny object, you'll see the entire reflection. So to compute that, you send a reflected ray. Whatever you see in that point is a reflected ray. So you see that ray R there. That R will go and bring some color. That also should be combined there. And you see the right side, the other ray, it goes and hits the darker circle on the bottom, and it is blocked from the light, so it will be shadowed there. But reflection will come from the third object on the top, which has lighting, which has reflection. So you can see at every point the ray goes and hits, whether it is the first object it hits, or the next object, you can have lighting directly comes from multiple light sources. You can have reflections, you can have other effects there. All the physics of what happens at each point is reasonably known to every one of you. who has done high school or some college physics. You just have to do this again and again and again. You do it recursively, that you send this ray, it hits something, that creates few more rays. Each of those may hit some other object, that will create some more rays. So it will keep going. Okay? And if you keep doing this deeper and deeper and deeper, you get a very rich picture. Because any object I see here, there are these bright light sources which light this object. But these light sources and the sun hit many parts of this scene, and light comes from there and hits this object. And those light reflected from there hit other places and reflect and hit this object. So multiple lights combine here. And the net appearance of that I see here is of all these lights together, not just one. So the more detail you add to it, the more realistic it will look. But you can imagine this is a very expensive process, but it will create very good results. So next. So we'll just compare one more, just click. Yeah, so ray tracing is what we saw just now. You simulate physics in steps by sending rays, creating the first rays, the next level rays, and the third level rays, fourth level rays, etc. And you can create nice pictures like this with shiny objects, with reflections. If you see closely, you see shadows, reflection, etc. That is ray tracing. You start from the camera and go out. Then the other picture there is about rasterization, which we talked earlier, where you think of the scene as multiple triangles or objects made of triangles, and you project each of them one by one to the camera and see how they look there. Okay. So the problem is go back. The comparison is very clear. The ray tracing is very, very compute heavy. We saw it ourselves. Every ray goes and hits, a million rays goes from there, they hit million objects. Each of those each of those intersections can create, say, 3 or 4 or 5 other rays, each of which may go an one object each, and those can create another 5, so it can multiply very quickly. Sometime later, of course, you will realize that going further is not of much use, because even if some light comes from there, the net impact on the original picture will be very small, so you'll have to stop. That is a practical matter. But in any case, it's a very compute-heavy operation. It produces very high-quality pictures. Okay? And rasterization is very fast compared to ray tracing, because they have created nice, beautiful hardware called GPUs, the graphics processor units, or used to be called video cards. These are hardware that can take a triangle and very quickly compute, do all the matrix calculations to project them onto an image and give some color there. So it can handle several million triangles in the scene. A scene like this will have 5, 10, 20 million triangles, and you can still draw it 50 times, 100 times a second. So you have 50 times a second means you have 20 milliseconds to draw once, the whole scene once. And that it can do, maybe 10 million triangles it can draw. In today's, even a simple video card that you can buy, a game card that you can buy can do that. So speed is easy here, but quality, you'll have to make some approximation. You cannot reflect, you cannot simulate all the reflections and reflections of reflections and all that very easily there. So where would you use ray tracing? Where do you use rasterization? In the beginning, I showed 2 pictures. One is from games. One is from movies. So what do you use in games? What would be more suitable for games? Rasterization or ray tracing? Those who think rasterization is better, raise your hands. Why is rasterization better? Because it's fast. And in games, you need speed. If you are playing a game, you are shooting somebody, you are clicking something. If it takes 2 seconds, 5 seconds, 1 minute for the response to come, you will get bored, you will go away. And in fact, you will get so nervous, you will click multiple times, and all kinds of funny things will happen. This happens when your computer slows down or something, right? Whereas, so you need fast, you need guaranteed frame rate. What they call in the game, they call frame rate. You need at least 50 frames per second. That is, the picture should change 50 times a second. Otherwise, you will see lag and you will lose interest in the end. So 50 FPS is a must, is not compromisable. Even if the quality is little low, if the game is interesting and you're moving fast, you don't see all the small light effects or some objects being painted little bit approximately compared to other objects, etc. You won't notice that because it's also engagement. Okay? Now, what will you use if you're making a movie like Avatar? How many of you think rasterization will be used for movies? How many of you think ray tracing will be used for movies? Yes, you are exactly right. Because in the movie, the situation is reversed. First of all, you go and you will see the movie in a theater nicely, or today streaming, but you will be watching for it. If you are streaming, you will stop it and say, oh, this doesn't look right, that doesn't look, you all criticize it. Okay? And movies have been made with very high quality film cameras from very old days, so you are very much used to seeing high quality pictures. Okay? And high quality pictures also give you sense of what is happening. So it's very important. So in movies, on the other hand, movie you have to create this computer generated image only once. The avatar will be rendered, or the movie will be created in the studios once, taking several years actually. Think of these computer generated movies are more expensive than live action movies where people are acting, because it's first of all, creating the right scene, right objects, right graphics object takes a long time. Then computation also is very, very expensive. But the good thing is you have to do it only once. After that, you just create a big video out of it and play it over and over and again. So there's no real time. Nobody is responding. Okay. So in high quality is required, you have to do ray tracing, but it will be slow. And rasterization is used when you need guaranteed performance, but the quality may be lower. But there's a lot of work going on computer graphics to bridge this, to bring this together. That is very, very fast ray tracing as well as more high quality rasterization. So that's part of research. Okay, next. Now we'll go to computer vision, the second part. Now what is computer vision? Next. Computer vision simply is interpret visual data, okay, images or videos. Now I show you this photograph that I took from an event a month ago. Now I ask you a question. Click, what is going on? You kind of know what is going on here. Anybody has, what dance is this? Bhangra. Okay, you all know. Next, click. How many people are there? Next. Who is in front? Who is back? Who are they? What do they hold? What is each person's height? You can ask all these questions from video, and all of you will be able to answer something. Okay, you will say this front person looks like 5 feet 8 inches or 6 feet. I mean, you may not be right. You are not very good at judging height, but you can make a reasonable guess. But all the other things are easy. How many people are there? You can count very easily. Who is in front? Who is at the back? Who is on the left? What are these people? Who are they in the sense? Now you may want to know the names of those people also. Okay. So how do you answer these kind of questions given an image? An image taken by your cell phone camera or some other camera, or that comes on the video, comes on the TV. How do you interpret it? Interpret can mean identities, numbers, heights and weights, whatever you want. You also want different information from the image at different times. Okay, next. So which is easier? Now computer vision or computer graphics? Which is easier? How many of you think computer graphics is easier? How many of you think computer vision is easier? Here you are somewhat wrong. So in computer graphics, as shown there, computer graphics is a forward problem, what we call a forward problem. The characteristic of forward problem is you have a lot of information, which is 3D world, for instance, appearance, etc. And some of it, and you project to a 2D image, and you are throwing away some information. Okay, so it's like you saw the pinhole camera, that equation of how 2D maps to 3D maps to 2D is exactly known. There's no ambiguity there. There's no errors there. Okay, which means you can just do, if you have compute, you can do at great detail. Whereas in the reverse, you are given a 2D image and ask what is the 3D world corresponding to that. Now you have to guess some information that is lost in the process of projection. And that is never easy. That's why it's called an inverse problem. Inverse problem where there's no unique situation that created this image. There are infinite situations that created an image. Whereas once you set up all the objects and put a camera somewhere, only one image will be created from that situation. Okay. Now just click once. Now you see 3 cars there. What do you see? Which car is bigger, which car is smaller? You see a giant car in the far away and some medium-sized car in the middle and a small car in the front. But in the image, I'm showing you that there is the 3 yellow lines. They are equal size. Click once more. Once more. So these images, those cars are of exactly same height and width in the image. Just because they are standing farther, your brain knows that farther objects get smaller. In the brain, you are actually somehow decided that the farther car is some kind of giant car, the close one is a small car. But in the image, if you look at the pixel, if you look at the XY rectangle that can cover the car, it's exactly the same. This is one of the demonstrations of the problem that from an image alone, I mean, we are not able to do. Can computers do it correctly? That's the question. Okay? So vision is an inverse problem. There are many solutions and there's no clear rules of physics. That's because, when you say computer vision, when human understanding is required, we don't know how we understand. We don't know how we look at somebody and say, this is person X. We can't clearly articulate how we look at somebody and say, this is a man or a woman. We will start saying, this is the reason, that is the reason. But I can create an image where all your reasons fail, but you don't fail. I mean, you can also create images where you fail. It's not difficult. But this is not an exact science. It's not known. Okay? Next. So how do we perceive? Yeah. Not clearly known how we perceive or understand things. Okay, some aspects are known, but a lot of the aspects are not known. So today's computer vision, after all the development, all the hard billions of dollars put into it, today's computer vision is not even as capable as a maybe 6-month-old baby who can recognize a few people, whether they are wearing some mask, some different clothing or lighting, day, night, etc. The baby is able to recognize. Today's computer vision system can very easily be fooled. Okay? Because it's a very, very hard problem. What happens here? What happens here in mapping an image to something that we understand is not known, and that's where the big AI or computer vision research is. Next. So computer algorithms can also be fooled, in ways different from how humans are fooled. Next. Okay. So in computer vision, they say, click once more. There are 3 R's, they say, just a little bit of details, not very important, but you can think of, I'll kind of say, you have to recognize, the computer vision, there are 3 types of problems, and they are related to each other. The easiest to understand is recognition. What is this picture? Who is this person? Okay? To do that, you need to reconstruct and say, what is the size, where is the person's face, head, etc. And you need to do that, you need to organize similar looking pixels into groups of pixels. And if you can do this better, you can do this better, then you can do this better. So these are not easy. Like I said, there are no hard and fast, simple mathematical rules that does that. With research, we have learned to do how to do that. Most of this comes from what we call machine learning. So here, some of the problems that computer vision looks at is face detection. You see every face has been marked with a rectangle. Say there is a face there. This is different from face recognition. It doesn't say who is that person. It says there is a face there. Okay? This you see on your camera or your cell phone camera also will do that. Next, the face recognition. Now, who is this person? Which is this chair? What kind of computer screen is it? What kind of bird is this? This kind of question. Even more complicated next is what are the... So this is these are the questions there. You see the picture where it's labeled as one is an iPhone, there's a spectacle, there is some book or whatever. Now you are detecting each object and not just saying this is a face, it's this person's face and so on. Next is read the emotions. Earlier in the first session they said, most of the communication happens not through verbally, you see, you get sense of what they are feeling. Somebody may be irritated, you sense it in your voice, they sense it the way they body language. Can the computer vision system can sense that? That's a huge challenge, okay? And third kind of challenge is 3D reconstruction. Click once more. You have given a multiple images, let's say. One image is not possible because, as you saw earlier, an object that is 1 meter away, a 1 meter long object that is 1 meter away will look exactly same in the camera as a 2 meter object which is 2 meters away. Because there is a dropping of the Z is not there anymore. You are dropping one. So if you are a small, that's what is happening in that car example. The same car was there in 3 different distances, you assumed. Which means if that car looks 10 pixels wide, but that far, that car must be a giant car. Okay? So this happens. So can you recover just from one picture alone? There is no unique recovery possible. It can be any number of options. That car could be a small car close by, big car far away, bigger car much farther away, and so on. But if you have multiple pictures, this can be solved. So given one or more pictures, can you recover the 3D model of the scene? That's the problem of 3D reconstruction. All the computer vision problem today, since there are no mathematical, clear scientific principles of which to do this, they all use what is called machine learning method. In machine learning, you have a black box, sort of a black box, which approximates a function that is go from input to output, and you initialize or you give the details of the function by giving lots of examples, lots of data, lots of correct examples, lot of wrong examples, and tell the system these are all the correct examples, these are all the pictures where dog is present, this is all the pictures where dog is not present. By giving many such systems, there are nice, beautiful machine learning models which have been designed in the last 10, 20 years, which will be able to say if there is a dog in this picture or a cat in this picture, etc. But that requires thousands and thousands of images, good images, bad images, that is positive examples, negative examples, and a model that is trained with a lot of, this is called training. You take all these positive and negative examples, and this is a machine learning model, you train them. So that when you give it a new image, which has not been seen before, it will say there is a cat there or not, 0 or 1, and it will be, today such systems are 99%, 98% accurate for common objects like cats, dogs, cow, airplane, ship, car, etc. That kind of common object has been very clearly done. Next. So now you can, we saw computer vision in some sense is inverse of computer graphics, is sometimes people say. Computer graphics is given a world, how do you create an image? Computer vision, ideal question is given an image, how do you create the world that generated it, which is a very difficult problem. But there are some areas where these are connected. One area is being called image-based rendering. Click once more. So you're given a few images like this of a particular scene. You can see this is called a garden scene with multiple views of the same scene. Click once more. You take all these and then you take a camera. This is all the images. Typically in computer graphics, you will say objects, 3D objects, cylinders, tables placed here and there, and then you place a camera in that scene. Here, all these images and place a camera, and can you get a new view? So many efforts in the last 10, 20 years where this has been made possible. Now you can get much more accuracy. Now you see the right side, you have a picture which look very, very realistic because every pixel is somehow taken from a camera image. It's not synthesized using light, object, reflection and all that. Okay? So it's a very realistic image and you can do this given, they have given many assumptions. We have been also working on it. Next, I'll show you a small video. It's a very active area in research, maybe 20, 25 years ago. Several methods work very well. So if you can do that, you don't need to model anything. Click a lot of pictures and then you can model that scene and go around, place the camera wherever you want in that scene. Next. So here is a garden, the same scene from about 40, 50 images. You can create a object. The scene, you don't really create the 3D model, but given another camera, where the camera is located and which way is looking, you can create a view. Okay? And what we did on top of that recently is this, treat it like a 3D object. You can select one of those objects there, remove it, just click on it, it'll play the video. Yeah. So you are seeing now it's just showing new video, just 40, 50 input, you can create infinite views now. Any viewpoint, you can see the camera moving closer, farther, etc. Now I stopped, I said remove that object. How to interact with it? That object went away, but its shadow hasn't gone. You see there? The object is not there, but shadow is there because it doesn't understand any physics there. Now I say remove the middle part. Next I'll remove that wooden rim, that wooden top, okay? And you can add some objects. So not just do given a large number of images, you can create new views, but also somehow manipulate the scene. This looks like graphics. To do the same thing in graphics take a huge effort. Okay? This is not, I'm not saying this is easy, but this is some kind of proof of that such things can be done even just by camera in very advanced machine learning method. Next. This is again, I'm just want to show you with what you're going to see is when you see in a movie some scenes, it's not created the way it's created. Some of it is real, some of it is virtual, that is created by the computer. Here you will see, click on this. You can see many such videos on the, just okay, this is only 2 media. You see very nice scene where somebody is sitting in the outdoor. The person is actually in a green room when camera being tracked there, and that 3D, the person was recovered somehow in 3D and transported there. Similarly, a scene like this, it looks like you see nice fog, nice some castle-like things, greenery. All these may be created separately. The castle may be created on computer graphics. The scene may be in the shot from camera. And here you see how, no, this is where it's taken. And you put a bookshelf there, some furniture there. The person is, of course, captured and rendered live. And this, I mean, these are some of the very advanced examples. But in movies today, there are some of the movies made completely on computer. And there are few movies that made only using a camera. Most of them have a mix of both. Some special effects at least. If not, this kind of combining. Okay, go to the next slide. Yeah. See, this is, I mean, this is the last one I'm going to just show. This is another video where you can see from just a video, a few videos, I mean, few cameras, 4 or 5 cameras from multiple directions. It's able to generate a 3D model, like the computer graphic model. You see, this person is doing very live action with very loose clothing, and what you see there is a 3D model recovered on the fly at the real time, okay, from the person, from the images. You can see there are a complex camera setup in the front, like that there are few on the sides and etc. This is not a simple setup, very expensive setup, very expensive computing is required, but it's still possible. You can recover, from live action, I'm moving around here, or with very loose clothing, it can all be captured. Okay, just go to the next one. We don't want to see the detail. Okay, so that's, in summary, I just want to say that, the computer graphics and computer vision combined is often called visual information processing, whether creating new visual information or analyzing the visual information, or sometimes combining the two like we saw in the end. These are a very, very important area because as human beings, we are primarily visual beings. We live in this world a lot dependent on our visual perception, and as well as visual, we create visual things, okay? And this is an very exciting area to study, research in, and build applications. There are lots and lots. You can just sit and think of applications of, if you have a camera, it can recognize anybody or any scene, anything. You can think of 100 applications in your life itself. So there are all kinds of applications possible. This has been a very actively researched area. A lot of development has happened in the past, but a lot more can come in the future. And I invite all of you to play with games. There are nice 3D editor, CAD tools, they call it, like Blender. These things you can install on your computers and create 3D worlds and then show how it looks from here and there. And there are some, computer vision needs a little bit more background to start doing, but there are still tools by which you can, there are tools by which you can just take a few pictures, show it around, and they will, you can immerse, you can send other cameras and see other views just like I was showing. I'll stop here, I'll take questions. I'll be glad to take any questions. Thank you very much for this opportunity. Questions, please.
How does rasterization handle refraction?
So refraction cannot be handled very easily by rasterization at all, but you can imagine how ray tracing can handle it very simply, right? And that's one of the limitations. There are models by which you assume when you are, when instead of just projecting, you say each point is a transparent, has some transparency to it, and then you can see where else it can come. But that's very complicated. You have to handle multiple steps. You first do the next scene and then bend it a little bit to look like refraction. So people do it approximately in a game or something because you want to have that effect. It'll be very, very approximate, sometimes wrong, but it'll still be fine. It'll be okay for a game. You will not notice the detail. As long as you see some reflection coming, or some refraction coming inside, you would be happy enough. So that's the trick of, the computer graphics, at least early computer graphics, is based on the fact that our humans and our eyes are very easy to fool. Okay, if you have engaging content, we don't look at the small problem. So that's the beauty of that. So you have to exploit that. And in a game setting, it's very easy. In a movie setting, you probably won't be happy if you see refraction that are wrong or somehow simulated. Thank you. Nice question. Yeah.
Good afternoon, sir. Sir, you mentioned that in rasterization, triangles are used, but why can't we use other shapes even when we miniaturize other shapes? They can also add to detail. So why only triangles?
Yes. That's a good question also. The reason is, the basic reason is triangle is the smallest planar entity in 3D. Okay. In 3D, if you take quadrilateral, you take any 4 arbitrary points, it won't lie on a plane. And if it look like some weird structure, and that is not a natural structure. So triangle is convenient. Now the real reason is, we need to have, when you do these graphics, you need to have what this triangle is called a primitive. That's the basic alphabet. You can create sentences out of basic alphabets. And you want to have small number of alphabets, not many alphabets. So a triangle can, earlier I said triangle is the simplest, smallest planar entity. So you can create any scene by using triangles, however small. Sometimes you have to make very small scenes. On the other hand, if you want to make a sphere or a cylinder, it's a curved object. If you can define a sphere exactly using a sphere equation, and you can somehow render it, okay? But handling a sphere as a separate entity, a cylinder as a separate entity, some other thing as a separate entity, adds to the software complexity. So you want to have minimal primitive, and triangle is the smallest, and that's why it's being used. And if you want to represent a sphere, you represent a sphere using 1,000 triangles. And if that's not smooth enough for you, make it 10,000 triangles, maybe 100,000 triangles. Finally, it will be 100,000 triangles. The sphere will look, the fact that it is not a curved object will not be obvious until you come very, very close. So triangles are able to approximate any curved object with large number of triangles, and they are easy to handle, and they can be optimized for the hardware. So these are the reasons why triangle has become practically the only primitive, only 2D surface primitive that is used in computer graphics. There more questions?
Hello, sir.
Yeah. Where is the question from?
Hello, sir. I'm here. Right.
Okay.
So thank you very much for the wonderful and insightful talk. So basically, I work in the area of fluid dynamics, where we use this high-speed imaging, and for a second we get some thousands of images. So to characterize the shape variation in such systems, basically for image analysis we use some ML-based kind of models and etc. But the selection of those models are a very critical aspect. So could you please add your comments on that?
Yeah. So, this is a big question. Earlier you heard about ML being used in material design and so on. So machine learning, there is no magic in machine learning. Machine learning is about function approximation. So if, there is when the functions are not so easy to describe, like the sinusoids or the logarithms and all that we're used to, and they are not easy to understand, then you say there is some complex function, and that's a machine learning model, which can be initialized. Its parameters initialized by a lot of data. Okay? So you need to use, there is a lot of work going on. You have to ask the machine learning people what is the capability of each kind of model, whether it's a MLP, that, multi-layer perceptron, or it's a convolutional neural network, or it's a transformer. These all have different capabilities, different requirements. What fits well with your problem is something that you have to ask the experts and experiment with yourself. There's no magic answer that I or you, anybody else can give. Maybe machine learning, people work over machine learning, what they approximate, etc., they'll know more. But you'll have to ask them.
Yes. Thank you.
Sir, so my question to you is, suppose you want to create animated film where you need detail and fast images. So will you use rasterization or ray tracing?
No, so if it's a film where you need a lot of detail, by film we already say that you only generate it once. If you generate it once, you can afford to spend as much time in generating it. So you can use ray tracing for it. Okay? In game, the problem is every image of the game is generated then and there on the fly. So, and that has to happen 50 times a second, which means speed is absolute requirement. And in which case you may have to forego some of the quality issues. So if you want to generate a film, that is, you do it in your studio and then you make a video out of it, an MP4 or some video out of it and show to others. Then it is, it's the right environment for using ray tracing there.
Sir, I wanted to ask that, as you said, like there are some ML models which will analyze the image and tell us some particular details about it. So can we do the inverse of that, in the sense that we give the details for an image and it will give us an image? So how does that work?
Absolutely. There are, this is a very, very good question and it's a very timely thing. There are the whole thing you hear now about generative AI. There are systems like, there is a tool called DALI. I don't know if you have not used, you should use them. DALI, which generates, you give a text image. You don't have to even give details. You just say, draw a scene where 3 rabbits are sitting with one elephant by a riverside. Just give this text, small text. It will generate a cartoon look-like image that describes that. So machine learning has been used very heavily for generative purpose, generating images, generating text, generating sound, etc. now. And this is very, very successful. So successful that we are all worried about it now. The Prime Minister himself talked about fake videos. Now you can combine, not just have cartoon-like images created. You can say, start with Sachin Tendulkar's one video and say, ask Sachin Tendulkar to say something else. Okay? And nobody will be able to say this is not a short film. Somebody take a camera, Sachin Tendulkar was saying this and somebody captured it with a camera. There's no way to distinguish between them. So this is creating something, creating a new video which really doesn't exist, which is slight difference from what the original video was. So this kind of thing, these are called deep fakes, the fake images, fake video, fake sound. This has been a huge problem now because these tools are available with everybody. You can, with a little bit of creativity, you can create anybody saying anything, a nice looking video, and many people will be fooled. They will think it's a real thing. So this is, it's a very active area and it's so successful, people are thinking it's dangerous.
So maybe we'll take one last question and
Sure.
close up.
Yeah, okay.
So my question is, human vision has limits and boundaries in order of 2 dimensions. Computer vision has no limits from 2D to 3D and graphics. So how can we modify the computer vision so that boundaries of human are able to explore all the dimensions, and is it possible to explore all the dimensions through the computer vision?
Yeah, I think that's not what you said is exactly not strictly true. The world is 3D. Okay, the world is 3D, that we know. Our vision, each eye gives you 2D images. But the one reason or one major reason we have 2 eyes is to know depth. Okay, if you close one eye, you will not be able to perceive depth as much as you can have 2 eyes. And we also move. If you move, even if you have one eye, by moving around, you can simulate having 2 eyes. So the world is 3D. Each of our eyes is kind of 2D. But we have learned, our brain has learned from birth how to convert 2D information to 3D. Sometimes we make mistakes, and since you saw in that car picture, you thought the car was a giant car, it is not. Okay? So we make mistakes because that's how we think. All the other images you have seen have convinced us that big things, if something is that far and it looks that size, it has to be much bigger than the thing in the front. So those are now our bias in our brain. So we are in a computer vision can do 3D reasoning, and it is doing 3D reasoning. But so some of those things are easy for computers to do because it's, 2-dimensionality is not very natural for us. If you ask me what is the size of this speaker, I can guess. I'm not very good at it. I cannot say what is the exact angle, etc. We are not good at it. We are much better at looking at somebody and saying, is this person, male or female? Is they looking bored, or they happy? They are crying. That we are, because those emotions are important to us, more important to us humans, and evolution has taught us how to recognize those better. So those are the extremely hard problems for computer vision. Some of these measuring problems like sizes or 2D, 3D, those are relatively easy by giving more information. In front of one image, you give 5 images, 10 images, which is all cheap today. Okay, I hope I answered some way. Yeah.
So I think there are more questions, but we'll kind of, maybe you can ask him after.
Yeah,
Because
I'll
we'll
be
move
here.
on to the next session. So
Thank you
thank
very
you
much.
very much. Many questions, so I hope you have some more time to
Yes,
talk to them.
thank you all. Thank you.